very much. Okay, so yes, as you can see, the title of my talk is SU2 hadrons on a quantum computer. And when we started this project, what we really wanted to do was to simulate some actual non-Abelian lattice gauge physics, some interesting non-Abelian physics on currently available quantum hardware. So the outline of my talk goes as follows. I will, of course, first introduce SU2 lattice gauge theory. I will just tell you what the fundamental elements are. And then, because we wanted to really to simulate it, I will talk you through the various steps that we took in order to make it accessible to the current hardware that we have available. So I will tell you about the gauge field elimination, how we map the model onto qubits. And then I will tell you about the specific simulation protocol that we chose, which is this variational quantum eigensolver. I will tell you about its feature and why we chose it. And finally, I will show you the results of this quantum computation that we did. So we did this quantum computation of hadron masses, so of the low-lying energy spectrum of the model. And then there will be a summary and an outlook. And I'd like to keep this informal, so you're more than welcome to interrupt me even with questions in the middle of the talk. I have no problem with that. All right. So since we want to simulate this model with quantum computers, the Hamiltonian formulation is more suitable, and the Hamiltonian formulation of SU2 lattice gauge theory has been known for a long time, since the 70s. So here are just the fundamental elements. We have a lattice on the sides of the lattice here. Leave the fermions, and because we choose the staggered fermion formulation, this specific discretization method, on every lattice there is either a particle sites or an antiparticle sites. And because we are choosing to simulate an SU2 lattice gauge theory, at every site I have two possible color fermions that live on them, either red or green, and here either anti-red or anti-green. Okay, and then on the link that connect the sites between the lattice, leave the gauge fields. And the gauge fields, because we, so in an Abelian theory, the gauge fields would be described would be just the electric field. But because we are in this non-Abelian theory, the structure of the field is much more complex, and it's described by a left and the right electric field, and by these U connection operators. Okay, so, but the form of the Hamiltonian, if you have ever looked at anything about lattice gauge theory in Hamiltonian formulation, should be quite simple and recognizable. We have here highlighted the fermion mass. So this is the energy that I have to pay in order to occupy the sides of my lattice with fermions. Here I have the gauge field energy. So this is the energy I have to pay in order to excite a gauge field state. And then most importantly, I have the kinetic term that describes the interaction between the fermions and the gauge fields. And of course, all of these terms have this local SU2 gauge symmetry. But these are just the three main elements of my Hamiltonian, and they describe the physics. And now I just want to say a couple of more words about the gauge fields, because I really want to highlight how this non-Abelian physics makes everything much more complicated, right? In an Abelian Schwinger model, the Hilbert space of the gauge fields is just this infinite ladder where you have an ascending and a descending operator. It's quite simple, but for an SU2 gauge field, for an SU2 lattice gauge theory, the Hilbert space of the gauge field can actually be interpreted as the same as a quantum rigid rotor with a total angular momentum J. So the states here are actually characterized by 3 quantum number, and they can be identified with total angular momentum, and then the projection of the angular momentum into a space fixed frame of reference and a body fixed frame of reference. You can see it's quite complicated, and the reason why there are these 2 electric fields instead of 1, it's exactly because the group is non-Abelian, and in a non-Abelian group, if you multiply by the left and the right, there are 2 completely different concepts. So the left and the right electric field have to be there are 2 different operators that have to be taken into account. Okay. But this you can forget immediately about, because as I said, we are going to simplify the model as much as possible. in order to simulate it. And the first step that we go through in order to simulate it is to eliminate the gauge field. Okay, so this is possible in general for every gauge field, as long as you're in one spatial dimension and you have open boundary condition. And this is essentially due to the constraint given by the Gauss law. So in the Hamiltonian formulation, the model is described by the Hamiltonian, of course, and this a series of constraints that we call Gauss law. And the reason why it is called like this is that if you go back to an Abelian quantum electrodynamic situation, if you look at this, you would see that it's exactly the Gauss law you've studied before. So it says that the divergence of the electric field is proportional to the charge that is in the sites, right? So you can imagine I have only one spatial dimension. Once I fix the matter configuration, I have to respect the gauge symmetry. The fields states are completely determined by what the fermionic matter look like. Okay. So this has been done before in this paper that I cite here at the bottom. And what they do is that they find exactly what the transformation is that allows you to transform this Hamiltonian that contains both fermion and gauge fields to an equivalent Hamiltonian that contains only fermionic field. So you can see here the kinetic term has been simplified. And most importantly, the gauge field energy, now it's expressed in terms of these non-Abelian charges, which are just expressed in terms of the fermionic field. Okay, so this is a huge simplification, right? Because I have highly reduced the number of degrees of freedom of a Hamiltonian. Okay, so the next step is going to be map into qubits, right? Because I have a fermionic Hamiltonian. In order to simulate it with, usually quantum computers have qubits available, I need to map them, and this is done via this Jordan-Wigner transformation. So what we do is that we take this lattice with the n sites. We have only the fermionic degrees of freedom left, right? The gauge fields have been eliminated through this transformation, and we just map them onto a single chain of qubits in the order that is shown by this blue line, right? So because I have these two possible colors for the fermion, for a lattice of n sites, in general, I will need 2n qubits in order to simulate all the matter. Each qubit will correspond to either a red or a green, or an anti-red or an anti-green, according to this ordering. Okay, so here is the final Hamiltonian that we obtain, and I've used the same color coding as before, so you can see here that I have a term that describes the mass, the mass of the energy given by the mass of the fermion. Here I have a kinetic term that describes the interaction, and here I have a green term that corresponds to the energy associated with the gauge fields. And here again, I want to highlight how the fact that we're considering a non-Abelian theory makes everything more complicated. So if we did this whole thing as has done before with an Abelian model, the kinetic term here, we have 3 body terms. In an Abelian case, it would be only 2 body terms. And in the gauge field energy would be, in an Abelian theory, all diagonal, so there would be only terms proportional to sigma z's. But in this non-Abelian case, I have these more complicated 4-body non-diagonal terms. Okay, but this is the model that we can simulate, and in general, this model is a platform and simulation protocol independent, right? You can take this and do whatever you want with it. What we decided to do, however, was to use this model to do a variational quantum eigensolver. And now I'm just going to explain what a variational quantum eigensolver does. So it's a hybrid quantum classical algorithm, which means that I need both a quantum processor and a classical processor. So the goal is going to be to use these 2 processors to calculate the ground state of a certain target Hamiltonian. So the way to do it is to use the quantum processor to prepare a parameterized ansatz state. So which is obtained by applying a certain parameterized circuit to an initial state. So that is going to be my guess and my test state. And then the quantum processor will prepare the state and measure the expectation value of the Hamiltonian that I want to minimize, right? So this this cost function is then sent to the classical processor that will have an optimization algorithm that will make some new guesses for what the best theta is, and then send them back to the quantum processor to again prepare the state and measure it, right? So there is this loop that is iterated, and hopefully, if my parameterized state is chosen well enough, at some point I will find the thetas that minimize the expectation value of the Hamiltonian, and therefore I have found what are the thetas that produce the ground state of the model that I'm looking at. So the reason why we chose to do this variational quantum eigensolver are essentially because, one, the hybrid, the variational nature of the algorithm makes it such that it's a bit more robust against certain types of errors, right? So let's say if they have a certain bias in my thetas in my circuit, these would be completely taken care of by the variational nature, because by the variational algorithm, because it will just find whatever theta give me the lowest cost function. And then because in this because we in the preparation of this parameterized answer state, we have a great amount of choice that we can use. So we can, first of all, we can adapt this circuit, this parameterized circuit, to whatever quantum hardware we choose to use. And we can enforce certain symmetries of the model in this circuit, so that the parameterized answer states respect certain symmetries of the model, and then the search of the ground state will be much more efficient. But all of this, if we know how to prepare our circuit well enough, right? Okay, so then let me now tell you about the symmetries of this spin model that I have shown you before. So these are all symmetries that derive from the gauge symmetry of the original model, and we have these three non-Abelian charges. Compared to an Abelian case where we just have one total charge that is significant. So all these non-Abelian charges should be zero in the states that I'm looking at. And then there is this symmetry that we call the baryon number, which essentially measures the imbalance between matter and antimatter in my state. And if you look at it, it's actually just proportional to the total magnetization of the state. Okay, so this means that if I can design my variational state, so this circuit U, such that all my ansatz state, all my variational states respect this symmetry, then I will be able to do a much more efficient search, right? And this is exactly what we do. So let me tell you about the states that we're looking at. We decided to look at the low-lying spectrum of the model, and we look both at the sector B equals 0 and B equal 1. So in the sector B equals 0, the ground state, that we will just call the vacuum, yeah? And then the first excited state we will call the meson, yeah? Okay. And then we will look also at the B equal 1 sector, where there is a matter-antimatter imbalance, and then we will call the lowest state in that sector the baryon. Okay, so given what I told you before, you can imagine that finding the vacuum and the baryon state are going to be easy, because I can isolate the specific symmetry sector that I want, and then I have told you already what is the cost function that I want to minimize, which is the expectation value of the Hamiltonian, right? So the ground state of each symmetry sector can be found just looking at the expectation value of the Hamiltonian. However, in order to study the meson state, you can imagine that this is going to be more complicated. And what we do is we modify the cost function. And the idea is essentially that we look for the meson state by looking at the correct symmetry sector, of course, and then we want to minimize the expectation value of the energy while minimizing the overlap with the previously found ground state of that sector, right? So of course, these eigenstates should be orthogonal. So the idea is that if this penalty weight beta is high enough, I will be able to eliminate all the components that are in the vacuum and then find the first eigenstate that has the lowest energy. Okay. And then in the design of our circuit, besides respecting all these symmetries, we will also introduce this further approximation to make life easier, which is we limit the maximum number of fermions that the circuit can create in each of the parametric state. So these are all the rules that we use in order to design the parameterized state that we use to look for these the states that we're interested in. And then the reason we are interested in these energy levels is essentially we just of course we want to calculate something that is physically significant. So we will look at the mass of the meson and the baryon, which is just the difference in energy between their energy level and the vacuum. Okay. Now we can design this circuit, but this circuit still looked a bit more too demanding for what we wanted to do. And so next I will tell you about the steps that we took in order to make this circuit even simpler. And then I will just show a specific example for the circuit of the vacuum, but we did exactly the same for the other two states. Okay, so this is what we call NISO adaptation, right? It's just simplifying the circuit to make it more accessible for the quantum processor. So here you can see the circuit that we designed in order to find the vacuum state. You can already see that it's for a chain of n equals 4. I need 8 qubits if you count them. And I have already enforced the symmetries. If you study the circuits, you will see that it will enforce the total magnetization equals 0. And then the other symmetries we were able to enforce, but you can see that here the variational parameters are not independent, and they are here the same exactly because we want to enforce these total non-Abelian charges. But we notice that we can do something even further, right? So if I write my parameterized states in this way, I can notice that I can separate two parts in my circuit. One that we call the dynamical part, which depends on the variational parameters. So they are changing all the time during the algorithm because the classical optimization is sending me new thesis to try. And then one part that we call the static part, right? So if you look at here, I have written the cost function. It's just the expectation value of the Hamiltonian over the variational state. We notice that the calculation of this part, of the static part of the circuit, can be included classically into the Hamiltonian, right? So essentially, we delegate all these operations into the classical part of the Hamiltonian so that the quantum circuit only has to do this part of the circuit. And this is already a huge gain because because I have reduced the depth of the circuit, so I have reduced the coherence time requirement on the quantum hardware. Okay, this is just the first step. The static part has been taken care of by the classical processor. The next step is going to be to notice that for this specific circuit, these two C0s can be commuted away. So what is left of the active part can actually be written as a separable states of certain qubits that are, which we call active. And this state will depend on the variational parameters, and certain states which are inactive, right? Because they do not depend at all on the variational parameter. So in the end, if we do this separation between these two separable parts of the circuit and we rewrite the cost function, we can notice that the only job that is left for the quantum processor is actually to calculate the active part of the circuit, depending on the variational thetas, onto a lower number of qubits, while all the parts that I have put in brackets here are calculations that can be delegated to the classical computer. Okay. So we have started with this 8 circuit qubit, and we end up with a 6 qubit circuit that has a lower depth, and this is what actually will need to be realized on the quantum hardware. And here you see the circuit, how it is plotted according to the topology of the quantum hardware that we've chosen to use, which is the IBM superconducting chip Casablanca in the case of the vacuum. Okay, so this is the actual circuit that is realized. Let me tell you about our results. Okay, so this is the quantum computation of the baryon mass for n equals 4. So you can see that so in order to calculate this, we had to calculate the ground state in the B equal 0 sector, so the vacuum, and then the ground state in the B equal 1 sector, take the difference, and we obtain the mass. And you can see here that the dots, the markers here, are the VQE computation, and the blue line is just the exact diagonalization results, and for a value of m tilde equal to 1 for a variety of values of x. And you can see that we actually find quite good correspondence. And the size of the error bar is actually mostly hidden by the marker. It can be seen here in some points and maybe here. So we actually get very good agreement. And this SU2 proton is just to represent these baryon states that we have calculated, right? Because the baryon state is in this P equal 1 sector. I have only matter particles, and this is just done in direct parallelism with the case of SU3 for an SU3 proton. Okay, and then we have the meson. As I said before, the meson is going to be a bit more complicated for a VQE because it is an excited state. So let me walk you through the various steps that we needed. So if you remember, first of all, we need to, and because this is more complicated, we did this with a very minimal choice for the lattice size, which is just n equal 2. So the first step is going to be to calculate the ground state in that symmetry sector. And this is what we do here. This is the circuit reduced according to the steps that I have already told you. So we first use this circuit to find what the vacuum state is. And these are the round circles, and we obtain these points. And then we know that in order to find the meson, I need both to evaluate its expectation value of energy expectation value, and this is why this circuit is needed for here. But we also use the previously found information for the vacuum state to calculate with this circuit what is the overlap between the vacuum state and our meson variational state. So this is what is done through this circuit. And you can see that, here theta v are the variational parameters that produce the vacuum state. And you can see that in order to evaluate this overlap, I need roughly a circuit that is about double the depth, right? So it's just computationally harder. Okay, and then using these two information, the expectation value and the overlap with the vacuum, we can finally find what the meson state is. And again, you can see you can compare it against the blue line, which is the ED value, and we find the vacuum energy, the meson energy, and finally in this plot we show the mass, so just the difference of the two. And also in this case, you can see quite good agreement. Okay, so this is the computation of the mass of the meson and the baryon, and I've told you how we try to simplify it as much as possible, and we did it by enforcing some symmetries, by choosing certain approximation, and by choosing specific values of these parameters, right, of my Hamiltonian parameters. But if I were given a futuristic quantum computer from space, there would be much more that we could do, right? Because the model has been already formulated. So we also try to dream a little bit. So I told you about this particle number approximation that we did, but for n equal 4, we also designed this other crazy circuit that would be able to, that gets rid of this approximation, and this circuit would be able to find the baryon state for n equal 4 for any range of parameters and in any situation. But you can see that it's a bit crazy, right? And again, but this circuit again could be separated into a dynamic part and the static part. The static part would not need to be realized, but you can already see here that it's a bit it's very hard, a bit unrealistic for within the currently at least. And then of course it would be interesting to go to larger system sizes. For larger system sizes, we decided to have this classical simulation, to have a bit of a brute force approach. And here we enforce actually only one of the 4 symmetries that I've told you about, which is the baryon number. And then we did some trial simulation for a larger size, n equals 6, and this seems that this should be able to work. So this is just to give some perspective. Okay, so just quickly, the conclusion. What I have told you about in my talk was I showed you how it is possible to give an SU2 lattice gauge model, which is complete with dynamical matter in 1+1D with open boundary condition, and how this model can be simulated. And I have showed you some actual quantum computation of the low line spectrum of this model via VQE. Future extension, they are very exciting, right? Because now that we have a non-Abelian model with matter and gauge fields, it would be for sure interesting to go to more dimensions. In the end, we will want to simulate something with 3 spatial dimensions, and that will be much more complicated because the gauge fields now can be independent degrees of freedom. So there will be, we need new techniques to simulate the gauge fields. And then of course, future extensions go to settings that are hard for classical computers to simulate. So for example, it would be to study real-time evolution. Now that we have matter in principle, we would really want to study, for example, hadron collisions, right? We would be interested to include chemical potential, which describes situation settings with really high baryon density. These are, and then it would be interesting to include topological terms, which having implications for high energy physics, and can be used, have been suggested to explain the baryon symmetry. And all these 3 settings are affected by this sign problem, and this would be where quantum computers would really shine and outperform classical computation. Okay, and with this I conclude my talk, and I thank you for your attention. And this is the team that I have been working on this project. Thank you.